Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
The awarding of the 2012 Nobel Prize in Physics to Serge Haroche and David J. Wineland jointly recognized their groundbreaking contributions to the study of quantum mechanics, specifically their work on measuring and manipulating individual quantum systems. This essay proposes to undertake a rigorous, section-by-section examination of their achievement, meticulously scrutinizing the core claims, methodologies, and experimental findings presented in their seminal work. It is the intent here to provide a critical, nuanced analysis suitable for an audience familiar with the intricacies of quantum physics and the profound historical consequences of its development. The objective is to assess the internal coherence, the validity of their arguments, and the enduring significance of their discoveries, illuminated through a narrative of their precise contributions. Section 1 Introduction and Framing the Challenge. Haroche and Wineland's work established experimentally accessible platforms for exploring several core quantum mechanical phenomena. The foundational principles had, for many years, resided primarily within the realm of theoretical contemplation. Their accomplishment lay in bridging the gap, making these fascinating notions experimentally testable, quantifiable, and subject to precise control. The conceptual framework inherent in their approach is a cornerstone of modern quantum information science. This science now promises revolutions in computation, communications, and metrology. This essay will, therefore, start by exploring the crucial introduction that sets the stage for the subsequent exploration of how and what they achieved. They articulate a need to move beyond the study of ensembles of quantum systems, which yield statistically averaged results, and toward the investigation of individual systems. This shift is vital for understanding the true nature of quantum mechanics, where the individual behavior of a particle is crucial. Their argument underscores the limitations of classical analogies. Classical physics operates under conditions where continuous measurements do not drastically alter the system. However, the very act of observing a quantum system fundamentally changes it. This core departure from classical physics, recognized in the historical development of the field, constitutes one of the most radical departures of 20th century science. They introduce the concept of quantum non-demolition measurements. These are measurements that reveal information about a system without significantly disturbing it. They frame the challenge how one can make such gentle measurements, and how one can use this information to manipulate and control these quantum systems. The introduction serves as a clear roadmap, anticipating the specific experimental methods and conceptual innovations that will Section 2 Trapped Ions and the Wineland Approach. This section delves into Wineland's contributions, focusing on the use of trapped ions as a platform for quantum experiments. The work describes in minute detail the techniques for trapping and manipulating individual ions, generally positive ions, within electromagnetic fields. The ability to precisely control the ion's position and motion is paramount, and they explain the use of radio frequency and direct current fields to achieve this goal. A key element that is revealed is the use of a specifically designed penning trap, or a similar configuration, to confine the charged ions within a small spatial volume. This confinement is crucial for isolating the ions from outside influences. A great achievement is their discussion on how these trapped ions act as cupids, the fundamental units of quantum information. The internal energy levels of the ion, for example, may be used to encode information with two specific energy levels, for instance, representing the states of 0 and 1. This section further details the techniques for controlling and manipulating these qubits. It covers a resonant interaction with laser light. This interaction allows for the selective addressing of individual ions, allowing for control of their quantum state. The description of the experimental apparatus is precise and comprehensive, emphasizing the importance of ultra-high vacuum conditions to minimize the interaction of the ions With gas atoms, the discussion shows the exquisite care given to every detail, from the selection of the ion species, such as beryllium or magnesium, to the precise alignment of the laser beams. The implications of this are clear. This allows for the creation of quantum logic gates. These gates are the building blocks of quantum computation, and are created through the careful manipulation of the quantum states of the ions. Wineland's work is shown to provide a practical pathway toward the realization of quantum information processing systems. Section 3, Cavity Quantum Electrodynamics in the Haroche Approach. This section explores Haroche's work with cavity quantum electrodynamics, or CQED. It describes the interaction between individual atoms and photons confined within a high-fineness cavity. The cavity, typically made of highly reflective mirrors, acts as a resonant structure, enhancing the interaction between the atom and the light field. Haroche's approach shows how atoms, specifically Rydberg atoms, possessing unusual properties due to their highly excited quantum states, are used. These atoms interact strongly with microwaves within the cavity. The section defines the concept of non-demolition measurement. This measurement is achieved by probing the field without absorbing the photons. The presence of the atom alters the cavity's resonance frequency. The shift in this frequency allows for measurement without significantly altering the light field itself. The experimental details, so carefully detailed, are the hallmark of this work. The process begins with the preparation of the Rydberg atoms. These are then sent through the cavity one at a time. The phase shift of the microwave field, induced by the atom's presence, can be measured. From that, we can gain information on the atom state. The central idea here is the possibility of observing and controlling the entanglement between the atom and the field. The exploration continues with the experimental demonstrations of the quantum Zeno effect. The quantum Zeno effect demonstrates that by repeatedly measuring a quantum system, one can effectively freeze its time evolution. This is another departure from classical intuition. Haroche's work also offers experimental verification of the creation and manipulation of entangled states. This is achieved here by coupling the atom field system and employing carefully tuned microwave pulses. The exposition of the experimental apparatus again shows precision in design that includes atomic beam sources, microwave generators, and sensitive detectors. The significance of these experimental demonstrations lies in the fundamental understanding of quantum entanglement and the potential for building quantum computing devices. Section 4, Quantum Measurement and Feedback. An important aspect of the overall achievement is the exploration of quantum measurement and feedback. Both Wineland and Haroche's work address how measurement affects a quantum system. Their discussion moves beyond the measurement problem, a philosophical puzzle. This puzzle concerns the nature of measurement in quantum mechanics. They present a view of measurement as an interaction that provides information about the system's state. In their work, they explain how the information obtained through measurement can be used to manipulate the system and to achieve specific goals. The concept of feedback is introduced. Feedback involves using the results of a measurement to influence the subsequent behavior of a system. In the context of quantum systems, feedback can be used to stabilize a quantum state, to protect it from decoherence, or to steer it toward a desired target state. They detail the use of feedback in stabilizing the quantum state of trapped ions. The specific implementation involves using the results of a measurement of ion position to apply a correcting voltage to the trapping electrodes. The objective is to mitigate any unwanted fluctuations and to maintain the ion's precise localization. Within Haroche's work, feedback is applied to manipulate the quantum state of the light field within the cavity. The measurement of the atom-field interaction provides feedback on the microwave field. Then, the experimental setup adapts to maintain a stable quantum state. The demonstrations of quantum measurement and feedback are critical for the development of quantum technologies. These technologies are founded on the ability to control and manipulate quantum systems with precision. The ability to maintain the coherence of quantum information relies on real-time monitoring. The ability to correct measurement outcomes is also critical. Quantum control becomes possible through a combination of measurement, feedback, and precise manipulation. Section 5. Entanglement, generation and manipulation. This section covers the core subject of entanglement, generation and manipulation. It is a central theme and is a critical aspect of both Haroche and Wineland's work. Entanglement, the peculiar correlation between two or more quantum systems, is one of the profoundest manifestations of quantum behavior. Its exploration is vital for quantum computing and quantum communication. In Wineland's experiments, entanglement is generated between the trapped ions and the motional states. They explain the use of laser pulses to entangle the internal electronic states of the various ions. The laser pulses achieve entanglement by coupling the internal degrees of freedom to the ion's motion. The creation of entangled states is confirmed via a series of carefully designed measurements. The outcome of these measurements is shown to be correlated, establishing an entanglement between the ions. In Haroche's work, entanglement is generated between an atom and the cavity field by controlling the interaction between the Rydberg atom and the microwave photons. They can prepare the atom field system in an entangled state. The section gives a detailed description of the experimental protocols they use to generate and characterize the entangled states. This also reveals the importance of quantum non-demolition measurement. An example is the ability to measure the field state without destroying the entanglement. The discussion then considers how the entangled states are manipulated using the precise control afforded by the experimental apparatuses. Laser pulses, microwave pulses are employed to modify the nature of the entanglement and to prepare the system in different quantum states. Their work showcases the ability to create complex entangled states. This represents a profound step forward in our capacity to manipulate quantum correlations. The work shows how these entangled states can be used for tasks such as quantum teleportation and quantum computation. Section 6. Quantum state tomography and characterization. The ability to fully characterize the quantum states of the systems is fundamental, as is the need for quantum state tomography. Both research groups address how to reconstruct the quantum state of their systems based on measurement results. Quantum state tomography is a process that is required to completely determine the quantum wave function. It involves making a series of measurements on the system and then using the results to reconstruct the quantum state. The essential approach involves making a series of measurements on the system with different orientations. These measurements provide information about the probability amplitudes of the different quantum states. The use of statistical analysis of the results is revealed. Through this, the quantum state is rendered precisely calculable. The description reveals the essential steps in the tomographic process. The need to make multiple measurements on identically prepared systems is central. The details include specific experimental protocols, such as the use of different laser polarizations or different probing frequencies, to measure various aspects of the quantum state. Another aspect revealed is the use of maximum likelihood methods to analyze the measurement data. This gives the most probable quantum state, consistent with the measurement results. They show that the tomographic characterization allows for the verification of the entangled states that they generate. The fidelity of the entangled states is demonstrated and accurately quantified. The importance of this achievement highlights the importance of being able to experimentally verify theoretical predictions, creating a closed feedback loop between theory and experiment. The precision of this characterization is shown as a powerful argument in favor of the entire experimental framework. Section 7. Decoherence and quantum error correction. Decoherence, the loss of quantum information, is a persistent challenge in the development of quantum technologies. Both Haroche and Wineland's work address this central issue. Decoherence comes about through the interaction of the quantum system with its environment. The experiments, therefore, are designed to understand and mitigate this unwanted interaction. In their experiments, a variety of decoherence mechanisms are meticulously studied. The key sources include the interaction with the thermal environment. The interactions include the collision with background gas atoms, and also the effects of noise in the control fields. The strategies for mitigating the effects of decoherence are described. The first step is to minimize the interaction with the environment. The experimenters create ultra-high vacuum conditions. They also take great care in shielding the system from external radiation. The next step that is revealed is the use of quantum error correction techniques. These protocols involve encoding the quantum information in a redundant manner. This allows the detection and correction of errors caused by decoherence. The detailed implementation of these protocols within the experimental context is presented. The discussion then explores the advantages of using different quantum states, encoding the information in a way that is less susceptible to decoherence. An example presented includes the use of different energy levels within a trapped ion to encode the quantum bit. This encoding scheme reduces the effects of certain types of noise. They show and discuss the prospects for designing quantum computers and quantum communication systems. Section 8 Applications and Future Directions. This section explores the potential applications of the work and the directions for future research. The focus remains on the internal arguments presented. It is the application of their work that truly defines the future. Quantum computation and the possibility of using quantum systems as the basis for powerful computation is the dominant idea. They detail how their experimental techniques, the generation of entangled states, and the ability to control and manipulate quantum systems are building blocks for quantum computers. Quantum computers promise to solve problems that are beyond the reach of even the most powerful classical computers. The work also points to the applications in quantum communication. Quantum communication systems utilize quantum entanglement to transmit information securely. Quantum cryptography schemes are described. These schemes enable the secure exchange of cryptographic keys. The principles of quantum metrology are another major application. Quantum metrology uses quantum entanglement to enhance the precision of measurements. An example introduced is the ability to measure very weak forces, or to measure a frequency, or the phase of an oscillating field with unprecedented accuracy. The research directions for future work include the extension of the experimental techniques to larger systems. The ability to generate and control entangled states now expands to a bigger number of quantum bits. The work indicates the ability to explore more complex quantum algorithms and to develop more advanced quantum error correction schemes. Several challenges remain, for example, to improve the coherence times of quantum systems, and to scale up the size of quantum devices. The work lays out the path forward. Section 9 Conclusion, Significance and Enduring Legacy. The work of Haroche and Wineland represents a landmark achievement in the field of quantum physics. Their work showed that the theoretical framework of quantum mechanics is not a theoretical construct only, but a field of rigorous and quantifiable experimentation. Their ability to measure and manipulate individual quantum systems opened the way to a new era of research. The meticulous section-by-section analysis here has provided an evaluation of their specific achievements. The creation of a new regime of quantum control has become a reality. Their work is a central component in quantum information, science and technology because it allows for the manipulation of individual quantum systems. The significance of their work lies in its ability to establish a framework for future research in quantum technology. It has enabled the generation and manipulation of entangled states. This has opened the door to quantum computing, quantum communication, and quantum metrology. The impact of their work has already been felt across various disciplines. The creation of quantum devices is now a tangible possibility. Their work has inspired researchers worldwide. The techniques that they developed are used in numerous laboratories all over the world. The impact on education is also immense. It has led to a greater understanding of the fundamentals of quantum mechanics. The enduring legacy of Haroche and Wineland is that they have provided the stepping stones for future generations of scientists. They have established a firm foundation upon which quantum technologies will inevitably be built. Their contributions will continue to shape the future of science. Their work, taken in its whole, is a monumental achievement.
We really appreciate you tuning into this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.